Cool. Thank you, Christos. Good morning, everyone. So, hope you're all settled down, had your coffees and breaks. So today I'm going to talk about visual concept learning, basically what Christos told from few images. Just my brief introduction. I currently work for Klarna now. I lead the fraud division, and I lead the data science division as well in the Berlin office. Till last week, I was working with OLX Group in the moderation team, basically dealing with moderation fraud in 40 to 50 countries, 55 sites, on a big scale. My past history is basically working in multiple software industries, and like last 5 years, I moved towards machine learning. If you want to contact me, there's my LinkedIn address. It's also on the last slide as well. So if you have any questions later on, you can put the questions there. So what I'm going to talk about today, what is basically few-shot learning, low-shot or one-shot, whatever that is. Some popular data sets that people are actually using to do the current research. Some approaches that have been that are popular approaches that you can use to solve this kind of problems. Some previous related work that is quite inspiring. And finally, some paper summaries. I'm going to talk about 4 papers today, basically like 5-minute introductions for each of these papers. So, zero and few-shot learning. What is it all about? So, it is about learning how to represent objects, in our cases, images, from very little samples, like very few instances of each object. It can range from 0. You haven't seen any of these images before. 1, you have seen 1 instance of these objects. And so on. You can see 5 instances of these objects, 20 instances of these objects. Let's say I give you an example of a fictitious animal called a zebra. It is a zebra, but with red stripes. And I show you one example of this image. As a human, I hope you will be able to distinguish all the zebra images from a stack of images. So let's see. For the next slides, I'm going to test on humans right now. I'm going to show you some examples of images. And finally, I'm going to ask you to predict what the animal is. Okay? So let's see how the human performs. One small thing. These images are coming from Board Panda. And I really do not know the authenticity of these images or the animals. So please do not quote me on that. The first one is a pink fairy armadillo. Okay? The next one is the Dumbo octopus. Third one is the Patagonian mara. Fourth one, a lamprey. Fifth one, a star-nosed mole. So now comes the test. What is this animal? Any answers? Second, if someone says second one. What you see here is like you haven't seen any previous examples of this animal before. So this is called a zero-shot learning. Now, a machine can be asked, what kind of animal is this? It is actually a fish. It is called a blobfish. But the next one, let's see. What is this one? See, very nice. It's a Patagonian mara, and see, the humans are performing really well. So the concepts. Next. K-shot N way. This is a very basic concept in few-shot learning. N is the number of classes that you can predict from. K is the number of instances that you're shown. So for an example, 2-shot four-way classification, you have 4 classes of colors, and for each color, you have got 2 instances. And from this, the machine needs to learn which color the reference image is from. So what did we learn till now? That humans can learn new concepts very fast without much training data. I just showed you one animal and you were able to predict that. But for deep learning neural networks, you need to show lots of examples, maybe hundreds, maybe thousands, maybe multiples of thousands. Typically, that leads us to the motivation for few-shot learning. Typically, what happens is if you just train an inception net or a ResNet or DenseNet, whatever that is, for one-shot learning, it basically overfits. Heck, even if you give hundreds of examples, it will still overfit if you're training from scratch. Neural networks has millions of parameters. This gives us the advantage that You can learn multiple number of functions. You can generalize, or if you show a lot of examples. But for one-shot learning, it basically is disastrous because it overfits on the sample data set. And that is the first point. It fails to generalize. Second thing, getting labeled data is expensive. Expensive in the terms of time, expensive in the terms of money. You can ask mechanical Turks to label your images. Then you need to verify, then you need to clean. You can ask universities to give you data, like comp cars. There are multiple different sources that you can that you can retrieve data from, but there's always like time and cleaning information, cleaning the data. Sorry. Third thing, adding domain information or feature information for your images. Let's say you're defining the quality of an image. How do you do that? Either train a neural network or add more features on top of it to say what is contrast, what is color, what the brightness is. So these kind of features, if you add to your network, it will not scale up well for other kinds of objects or other kinds of images. Fourthly, the thing is all these gradient descent methods that are currently employed in CNNs, these are just not made for to work under the constraint of a less number of samples. So you need to give a lot of samples so that it can properly gradient descend and find the lowest minimum in your loss. The last thing is when you are training a neural network, you kind of randomly initialize the weights of your neural networks. This also hampers your training because in order to converge, it needs a lot of epochs. So if you have proper initialization of weights, your networks can converge faster. So these are some of the problems that are being solved using few-shot learning. So some of the popular data sets that people are actually using, that researchers are actually using to solve this problem. The first one is called Omniglot. This was made by Bernard Lake in 2015. These images are basically 105 cross 105 grayscale images. In a total, there are 1,623 characters from 50 alphabets. And each character is handwritten by 20 humans. So for each 1,000 characters, you have 20 handwritten images that you can learn from. The alphabets range from different languages, Hebrew, and there are some fictitious languages as well, Futurama, Orat Beige, thing here. And the second, the newest papers, like from the last year, they are currently using ImageNet, mini ImageNet, because they resemble more real-life pictures. Omniglot is like the MNIST of few-shot learning. Some approaches and related work. So there are two basic approaches that you can use to do few-shot learning, as in if you have a constraint of number of samples. First thing is data-based. This is very easy and practical as well. And the second thing is metric or parameter-based, which I'm going to talk about next. Data-based, I touched on this topic before, but you can tap into external sources. Basically, you can download images from Google search. You can download images from, if you have alliance with the university, you can get some data from there. And you can also pay some companies to label, to get some data, labeled data. Secondly, you can generate new labels by semi-supervised learning. So if you have some labeled data set, you can do a nearest neighbor, and you can label some of the unlabeled data set as well. This is semi-supervised learning. A colleague of mine yesterday, Andreas, he talked about GANs to do semi-supervised learning. The third thing is actually GANs. You can use GANs to make fake data set, actually. A very good research paper is from Facebook AI, hallucinating features for using GANs. And then comes the metric or parameter-based. There are 4 papers. I just chose 4 papers. These are the most popular papers that you can get. First thing is from Siamese networks by Koch, Zemel and Ruslan Salak. Second thing is memory augmented networks, matching networks, and meta-optimization. I'll talk in deep in the next few minutes. Right. So, related work. These are the inspiration works that has been done before people jumped into few-shot learning. The first papers came from Fei Li in between 2003 and 2006. He talked about Bayesian learning, and basically what he told was you can previously learned classes can be leveraged to help forecast future ones. A very Bayesian concept, but in terms of images. Second thing was Bernard Lake. This paper basically revolutionized the few-shot learning methods. His paper was about hierarchical Bayesian program learning. Basically, concept learning through probabilistic programming. So if you see an example here, this is a Sanskrit letter Om. So what he's trying to do is he's trying to decompose this full letter into individual patterns here, and also the pen strokes. So basically, he's giving feature information to the network, and I'll also show you the evaluation. And with his work, he got very close to human performance. Now comes the paper summaries. So the first paper summary is about Siamese neural networks. This is only for one-shot image recognition. So what these guys do, this is a very ingenious paper back in 2015, just after Bernard Lake's paper. What these guys did was they created verification networks. So in your test task, you basically give image pairs. Basically here, a football and a football, and the classifier needs to predict if it's the same image or a different image. So you give image pairs, football and crocodile, different, elephant, same, elephant, crocodile, different. So from your sample set, you just create test pairs, and then you feed it into the network. He also did some experiments with voices, and trying to decipher if it's the same voice or different. Finally, during the test task, you also need to give test pairs, because it's obvious. So you give a basketball and a polar bear, different basketball, and basketball should be the same. So this is your test task. So how does this network look like? Basically, it's a Siamese network, Siamese twins, as you say. It's a very small CNN network, very simple. Some convolutions, some max pooling, some ReLUs stacked on top of each other. So you feed the image, omniglot in this case. Finally, you get a 4096 vector of the image representation. What you do is you take the equilibrium distance between the two images, and then you make a sigmoid on top of it. Basically, sigmoid makes a binary classification if it's the same image or a different image. Basically, two representations, are they the same or not? I'm not going deep into mathematics because time constraint, or also the code, because there's a lot of code available online as well. So you can just hook up onto that. So here you see the evaluation metrics. What it says is the second one is HBPL by Bernard Lake. If you see the performance is very close to humans. And if you see the convolution Siamese net, this was done by Cox, Emil, Salak. The references are there. They reached a performance of 92% accuracy. The baselines were basically KNN nearest neighbors, which is here, which reached around 21.7. All right. So before going on to the next, so this are these summaries that I'm going to give you. Very short, very brief. Second paper. Before I go to the second paper, I'm going to talk about some concepts because all these next papers, they use these concepts. The first concept is of episodes, because when you're trying to train a new network, all the new papers will try to use episodic learning. So what is an episode? You show an image, and in the next time step, you show the label of the image, and then you go on. So you show an image, you get the label. And basically, at every time step, at the next time step, you're asking the network to predict the label. And then if the prediction is wrong with the class, then it backdrops and updates the weights of the network. Same as that. And typically, people have been using five classes of images in one sample. These range from 5 to 20. The next concept is about meta-learning. Meta-learning it's a big topic. It can be a paper on its own, a topic on its own in PyData. What they do is, what is meta-learning? Meta-learning is about learning from, trying to combine learning from previously learned data to a new learner. So there are two optimizations that you need to do. The learner which is learning a new task, and the meta-learner which is trying to train the network, trying to train the learner. So simple. There's a learner, there's a classifier that you have built, and then you want to hook up a meta-learner which is trying to teach this classifier how to proceed further, basically how to optimize the weights. In this example, this is a paper from Ravi and La Rochelle, which I'm going to talk about in the end. They're trying to do meta-learning here and meta-testing. So in here, you see that they're also doing episodic learning of 5 images. So you show 5 images here, and then in the test set, it can also vary 2 to 5. This is very different from the conventional machine learning that we try to do here, as normally that we do. Normally what we have is it's a whole data set. We split it into training and testing. But basically, the classes that you have in training should be there in the testing data set. Meta-learning is very different because you train a certain number of classes, but on the testing set, it can be a different class. Sorry, in the meta-testing phase, there can be a total different number of classes. So if you see here, there's some kinds of dogs here, some kinds of mushrooms, but in the meta-testing phase, there's some cups, tigers as well. So the samples that the network sees during the testing phase doesn't need to be the same in the training phase, doesn't need to be the same in the testing phase. Next concept is about neural Turing machines. This was done by Graves from DeepMind in 2014. What he proposed was you have a neural network, which is the controller, and what you teach this controller is basically store information into the memory. So once you get information to this neural network, it saves it into memory, and whenever you ask to retrieve the same information, it goes into the memory and gives you the information. And it needs to be very fast. You can also update memories, but these neural Turing machines are very location-based optimized. So you have indexes, and then whenever it asks for the same information, it should retrieve from the last location. So normally, in neural Turing machines, you fed the network sequentially, so you had sequence of data, and what this was optimized was last used memory location to give the outputs. All right? So these concepts basically triggered the next papers. So the next paper is about one-shot learning with memory-augmented networks. This was also done by DeepMind fellows, Santoro and others. So his paper was also very genius. So he said, OK, I'll use a neural Turing machine, but instead of just optimizing using location, I'll try to optimize using image representations and similarity between image representations. So here in the task setup, you basically give episodes, and in different episodes, you shuffle the labels, the classes, and the samples. Right? So we have five classes now, and the next episode there can be shuffled. The images can be shuffled, or there can be totally new classes. And what he did was he hooked up an NTM on top of his LSTM network, and you fed an image here, and in the next time step, you basically fed the label. And then he asked the new NTM to store the representation of the image and the class. And basically, the chain continued, and at every time step, it asked what the class label is. And if the class label was wrong, it used to backdrop and update the network. So this was kind of the summary of this paper. In the evaluation phase for Omniglot, he got, so you see that at the first instance of these objects, of these Omniglot images, humans were doing around 34.5. Using his memory augmented network, he got 36.4. But if you see the second one, the second instance of this this network basically revolutionized and made it 82.8. So from second on, it basically jumped. The accuracy levels basically simply jumped, and there was like a lot of commotion. Okay, this is really nice. So that brings us to the next paper, matching networks. This is done by Vinyals. He's also a DeepMind fellow. What he did was also ingenious. What he did was, okay, I'll use an NTM. I'll also use an LCM. But instead of just using a similarity between images, I'll put an attention logic. And also what he proposed was training and test conditions must match. So if you are showing five sample of images in one bucket, and during the training phase, the test conditions should also match. You should also show 5 classes in the test. Thirdly, I have not written here, he said humans should not be considered as baseline here, because humans have learned throughout their life cycle how to recognize objects, images, letters. Basically, if I'm given a Greek letter, I kind of know it's a Greek. If it's a Sanskrit, I kind of know, okay, it can resemble a Sanskrit letter. So he said humans should not be there in the evaluation. So a bit of maths here. So what is there? What is a sample? Sample is a set of images that you see, X and Y. You have some images, and you have some target values. What you need to do is make a classifier for a new image that should have a class label from one of these sample images. So give a classifier which defines a probability distribution, P, for a target for a test image, for a Y which is present in the sample data set. So this Y target class, what is it? It is basically an attention mechanism, which is a softmax on the cosine distances. And so this basically is the chunky part of this paper. The Y here is the one-hotted encoded values, and that's about it. So here also, what this G theta and F theta, these are also LSTMs, but these are bidirectional LSTMs. And in bidirectional LSTMs, the sequence really matters. So you can't shuffle the images. You need to have, if you're doing bidirectional, the images that you feed in should also go in the same sequence backwards. So that was it. And the evaluation, if you see now, from the memory augmented neural networks, you see the performance of 82.8 and 94.9 on 5 accuracy, and then in matching networks, you basically see he made a 98.1. This was mind-blowing at the time. He also said, okay, omniglot is good enough, but we need to do on real-life images. So he took ImageNet, and he got a score of around 46.6, and for 5-shot, he got 60% accuracy. So very well so far. So if you have already got 98% accuracy, how much can you do better than that? And that brings us kind of to the next paper, optimization as a model for few-shot learning. This paper is kind of it's like ingenious, right? Because in all these previous papers, you had multiple networks that you need to put into production. And as a machine learning engineer, I want to make my life simpler. So I need one, if I'm just doing image classification, and if I can just do it in one network, I will just go for that. So this was done by Lavi and Arshel. I think they were, at that time, working for Twitter. I still do not know where they are right now, but Arshel you can find a lot of YouTube videos. So what he proposed was he used an LSTM-based meta-learner and tried to optimize a CNN. So in a CNN, you're learning all these parameters and weights, right? So he said, okay, for all these parameters that are there in this network, you fit it into an LSTM, and I'll propose you the next parameter update. Instead of using gradient descent like Adagrad, Adam, or whatever, because these are really slow. So this, he just hooked up an LSTM meta-learner to just propose the next network weight. The next thing that he proposed was initialization of the network from an LSTM as well. Because if you randomly initialize a CNN, it will converge much later and after a lot of epochs. But if you hook up an LSTM and put the weights, initialize the weights from there, it can converge much faster. Basically, you have already a meta learner there, and you from a different task, and then you hook up to a CNN which is learning another kind of images, and it will optimize better, as said from the paper. So this is very simple structure. So on the top here is the learner, and on the big blobs are the meta learners. So the learners are a CNN. You feed in an image and a target class, and the deltas and the loss functions are basically for each sample, which contains multiple images. You get a loss function. For all of them, you feed in the loss to the meta learner, and the meta learner will just propose the next parameter updates to the CNN. So in one blob, it will give you the whole parameter updates, and the cycle chain continues. And finally, you have a good network. And this, on the right-hand side, you see the test task. So what he did was his paper kind of got to the same performance as before, Vignel's of matching networks. But then still, for me, this is really ingenious because in the end, you get one CNN trained really fast, and then you can just put the CNN into production, and your job is done. And yeah, that's about it. There are some more papers that you should look into. One thing is, the last paper that I read was one-shot imitation learning. This was about recognizing human actions. So if I'm trying to pick up a bottle, the machine should be able to learn it from one instance by just seeing how I pick up this bottle. It should learn that. And this network is trained on many other actions, and just showing one action, these guys are trying to train a network. And I think these are also working for DeepMind. I'm not sure. The next one is from, I told you before, low-shot visual recognition by shrinking and hallucinating features. In this paper, they are trying to use GANs to hallucinate and create fake images to train the network. This goes into the data domain and not in the parameter or metric domain. And there are some code bases that you can hook up into. NTM's neural Turing machines from this GitHub code, Siamese networks. This is a very good blog post using Siamese networks just to make a test pairs and making a Keras model. You can just make a Keras model and then get equivalent distances from the feature matrix. Last thing, the business value. What do you do? Okay, here we are doing few-shot learning, but why should we do it? The first thing is you would have used your new Samsung and Apple phones, and now they do facial recognition, right? They have many other features put into place, but one of these things is they just take one picture, and from one picture, they can recognize if it's the same face or a different face. So this is one example. For OLX, it was trying to moderate items which are not shown. So I come from a fraud domain, and the number of classes that we have for fraud is very less, and for images, even less. So how do we train a network? And so we have to follow these kind of principles, either going to the data domain or the metric domain to create a network. And that's about it. If you have any questions, I hope I finished on time. I think I have 5 minutes more left, but if you have any more questions, please go ahead.
I think we have 10 minutes for questions, so
yeah,
please.
Okay, I have a question about the siamese network.
Yeah. Can you just wait for the mic, please?
I have a question about the Siamese networks. So there were two convolutional nets, and are they trained independently, or are they the same networks, or how it works?
So the question is, when you're training a Siamese neural networks, do you train both the networks at the same time? And the answer is yes. So you backprop at the same time.
Okay.
So you have two networks. Basically, you can easily make it using Keras. You have two CNNs. and a merge layer at the bottom. Basically, you have a sigmoid layer, right? So the whole backdrop should go back to the top, to the first layer. So you train the whole network in one go. So you put an image pair, you go through the CNNs and max pooling everything, you get a representation, and then you need to put a sigmoid layer at the end. And if the sigmoid layer is making a bad decision, it needs to go backdrop and fix all the weights in the networks.
Thank you.
Any more questions? I hope I made this concept very simple and plain English. I didn't want to put in a lot of maths because maybe I would get stuck as well. Cool. Oh, here.
Kind of following up on something that's already been mentioned, but can you talk a bit more about like different applications that you've found for this kind of approaches so far, maybe even in your current work?
So this gentleman is asking if what are the current business values of what are the practical applications, right? In my current job, it is basically in OLX. OLX is a classifieds market, so you get a lot of objects, a lot of listings coming to you. So if you want to sell your jacket, if you want to sell a bicycle, if you want to sell a flask or something, or a computer, you get lots of categories coming in. Sometimes there are new categories coming onto your platform, and you need to learn them, basically, so that you can improve the search on the platform. Second thing is moderation. There are some kinds of objects. Let's say we are dealing with so many countries, and there are certain forbidden items in every country. In Poland, it is the cigarette vaporizers, okay? So you cannot sell cigarette vaporizers in Poland. And you need to recognize these objects. Sometimes you can get these images easily from Google, but sometimes there are not so many images available. So you need to do these kind of approaches there. Industry standard is mainly about facial recognition and trying to make CNN networks just learn faster using some small number of examples. Because in the end, if you're training a neural network, you need to learn on a lot of examples. This goes on to self-driving cars as well, because you need to learn on a lot of you need to make your car go around a lot of tracks, get a lot of images, trying to learn from them. So if you can learn it faster, it's always better.
Hi. I'm coming from the insurance industry, and so the problem we are facing in fraud fighting is to recognize the same damage, which is always unique. So do you have any recommendation, maybe which one of the structures that you presented would be suitable method, since we also have very few instances of the same, let's say, class, which is a damage?
Practical approaches that I would say, these papers are really good, but then it is very difficult to implement them. If you can implement them, I'll repeat the question. So the question is that in insurance, people are posting pictures of car damages, and they might not be, and these all damages are quite unique, because you can hit a car in any direction, and they might be like front bumper. So how do you classify them? Because there are very few examples. My current approach would be to use a data domain, trying to hallucinate features from images, basically create more data set to train a network, because all these, the research trend that is currently going on is still going on, and these are still very academic, not production ready yet. If you can use the Facebook paper here, the second one here, to hallucinate features, this can really help you. But still, you have to implement the paper from scratch. So I think there's a parallel track how to implement a paper and what are the learnings from that.
Is it okay if I have another question? So what we were trying to implement is a paper on deep ranking. Do you have any experience with it, with triplets of images?
Triplets. Triplet loss was I think invented by Facebook. That they were trying to do facial recognition in all these pictures. So I make a tag on my image, and then it was trying to recognize all these images in all my pictures. That is also very good, but then you need to have always in a triplet when you're training this triplet networks, you need to create all these triplet triplets, right? So you need to have two images same, and the third image a different image. In order to, this is a very good network, but to get this data set is very difficult. You need to work a lot to make this data set, and that is the most problematic way. For Facebook, it was quite easy because you get so many images on their platform, and they have these software engineers who can make this data set to train on. I hope that answered your question. It is, of course, not the perfect answer, but yeah, you have to try your ways to do it.
Thank you.
For the last paper you presented, there was this meta strategy that provides the parameters. Could you explain a little bit more how this is trained, or how it knows in which way to optimize the parameters?
Okay. So yeah, just put me here. Let me see if I have this paper somewhere open. So let me see here. So basically, this is the picture here. As I if you read the paper, it can explain you much better, and you can come up to the desk, and Oleg's desk, and I can explain there. So these are in different phases. So here you have a CNN. You feed in your images. Okay, these is just not one image. You're feeding in a sample of images. These sample set can vary from 5, from 1 to 10. When you feed in all these pictures to the CNN, you're getting a loss on the labels that you predicted. Once you have got the loss, you put this loss into the meta learner. Yes, which you put in the meta learner and which predicts the final parameters. Now the thing is, CNNs currently have a lot of parameters. So if you just take an inception net or a ResNet, this kind of things will not work. You need to have a very simple network, very simple CNN, so that your meta learner can learn all these parameter updates. Because if you just choose a big one, this meta learner will explode and cannot do much. So it does a lot in parameter sharing from different phases and trying to give you a parameter update. And if you read the paper is not very, you need to read it multiple times to basically understand the maths behind it. But I really like this concept because, as I said before, you get one CNN in the end. But this is just not like Inception net. This is they train like a 3-layer or 4-layer network, and it is specified how the training strategy went. Okay. I hope there's one more question. Okay.
Yes. So I think in the first paper you mentioned that you were comparing, let's say, elephants with elephants and elephants with a different animal. What kind of detail can you recognize between the two images? Let's say you are comparing, I don't know, documents. Lines in between. Can you also make an assertion in this direction, or is it too detailed?
If you're trying to do in that case, so the question is, okay, the Siamese networks, we are trying to do very distinct, conceptual, different images from an elephant to a football. What if you have conceptually same kind of images that you want to differ? In that case, I would go for fine-grained classification. Not using Siamese networks. You can use Siamese networks as well, but you need to do fine-grained classification. And there's a whole different domain on doing fine-grained classification on conceptually similar kind of images. This Siamese network you need to train in a lot of epochs. to see if it kind of works. You need to test it out. I haven't done it, so I do not have a practical example that can help you out.
Okay, we are out of time for questions. I'm sure Vaibhav will be around for more questions.
I'll be at the OLX desk around that, so if you have more questions, you can come up to me.
So, yeah, thanks again.
Thank you, Christos.